Okay, so I'm going to start talking about kinematics, and to do that, I'm just going to do a little analogy right now. It's 70 degrees, and the temperature is going up at 4 degrees per hour. What will the temperature be in an hour? Well, that's pretty easy. If it's going up 4 degrees every hour, then it's going to be 70 plus 4 times 1, 74 degrees, okay? But if we think of the temperature plotted as a function of time, that 4 degrees per hour just keeps going up and up. So what will the temperature be like in 20 hours? Oh, well, 70 plus 4 times 20, it's going to be 150 degrees. People are going to be dying. So we know this is flawed a little bit. And so we've got some dynamics here. 70 degrees, we can think of that as when we talk about kinematics or the physics of describing motion. 70 degrees is kind of like a position, right? 4 degrees per hour, that's like how much the position changes over every unit of time. So that's like a velocity. Well, we don't just have constant velocities. That's going to be changing. So maybe in an hour, it's only going up 1 degree per hour. So we really have a thing called acceleration that describes the change in position per unit time, how that changes per unit time. So those three things are the things that we're going to be talking about in kinematics. We talk about these three: position, velocity, and acceleration. Position is just what it is. It's where you are, okay? And it might be on some coordinate axes or a number line, but that position is, we call it x. Velocity is the change in position per unit time, how fast the position is changing. Acceleration is the change in velocity per unit time. We're going to talk about calculus later, and we're going to talk about derivatives. And the velocity is the derivative of the position with respect to time. The acceleration is the derivative of the velocity with respect to time. And it's also the second derivative of position with respect to time. Now in kinematics, we want to be able to look at things in different modes, okay? We want to have a really strong understanding of problems and of kinematics. We want to be able to describe the situation that frequently comes with the problem itself. Block starts with a velocity up a ramp, slows due to acceleration down the ramp, velocity decreases, and at its greatest height has a velocity of 0, then speeds up down the ramp. Okay, so that's a description of what's really happening. Okay, and we're going to talk about acceleration later. I don't expect you to fully understand this problem. I just want to talk about the different things we're going to do with each problem. You want to be able to describe it. You want to be able to draw a picture of it. Okay, and this is a rough picture of a block going up, slowing down, then speeding up in the other direction. We're going to talk about what those dots mean. We want to be able to represent it graphically. Okay, and this would be, again, we'll get to this point where we're doing, in between this and the next lecture, between those two things, we're going to be looking at position, velocity, and acceleration graphs and how they relate. We'll be able to go from one to the other to the other. And then we want to be able to model it. And when I say model it, we want to be able to say true things, write equations, representations, list variables, things like that. So we're going to use and I apologize for the symbols there that didn't work out, but we're going to use the mathematical descriptions. And I'm going to say very frequently in the AP Physics C course that we want to be good at physics as a second language, because when we look at word problems and we try to solve them with our words, that's where we get into trouble. But when we can translate the word problems into graphs and mathematical models and descriptions, we can solve them in the mathematical world and then translate back to our first language. Motion diagrams are a useful way of picturing motion. Here's an object here. It's going at a constant velocity, steady velocity across the screen. If we did a motion diagram for it, it's like a strobe light flashing on it. So at the beginning and after every, let's say, second, equal intervals of time, and we could see it would travel the same distance in every equal interval of time. So that would be a motion diagram for a constant velocity. Now this next one is going to accelerate it slow, faster, 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 faster. So early on in one time interval, it didn't travel very far. In the next time interval, it traveled a little farther. And so each of these intervals, it's traveling a greater and greater distance between those two. So motion diagrams can be really helpful for picturing how things move. So let's look at this. I want to introduce the concept of position and displacement. Position we usually write with X or Y if we're doing 2 dimensions. Displacement is the difference, the change in position. We call it delta X, the change in position. All we need is 2 points to find a displacement. Okay, so here a ball is rolling to the right and slowing down. A picture for this might look like this, like a motion map. Okay, and at 0 seconds, it's position 0. At 1 second, it's position 4 meters. We'll call it meters. At 2 seconds, it's position 6. At 3 seconds, position 7, etc. And we can graph that motion, but there's a delta X. There's a displacement. From 0 to 1 seconds, the displacement is, it has moved 4 in the positive direction. And the way we can do this is we can take that final position minus the initial position. Delta anything is going to be the final minus the initial for whatever time interval we're talking about. Okay, so it's 2025 and I'm 65 years old. In 2023, I was 63 years old. My change in age is 65 minus 63 equals 2. It wouldn't make sense to do 63 minus 65. It's always the last minus the first. So 4 minus 0 would be my delta X. For this one, 6 minus 4, 2 would be the delta X. So we can graph that. We can just put data points there and we can do a trend line. But we can also say some things mathematically. X0 at time 0 is 0. At time t equals 1, X is 4 meters. Delta X is X minus X0. Let's just do for a sample from 1 to 5. We don't have to do, we can do between any 2 times. From t equals 1 to t equals 5. Well, at t equals 5, it's about 8 meters. At t equals 1, it's 4 meters. So the final X minus the initial X0 at 8 minus 4 is 4 meters, is the delta X. That's the displacement. We're also going to talk about distance. Distance is the same kind of calculation, but for distance, you have to actually consider everything that's happened along the way. So in this case, the distance would also be 4 meters from 1 to 5 seconds. But if it started moving in the other direction, the distance is going to be greater than the displacement. Displacement, you only need the 2 points. Distance, you need to know everything that happened in between. I am sitting in a chair. I went out for a walk earlier and came back to this chair. My displacement is 0. I'm at the same place I started. My distance is several miles. So distance and displacement can be very different. I walked 5 meters east and 1 meter west. What was my distance traveled? Well, my total distance, I walked 5 meters and then another meter. That's 6 meters. What is my displacement? Well, there we've got to really think about the vectors. I moved 5 to the east and 1 west. An easy way to do this is to pick a positive direction. And so you can see my displacement is going to be less than 5. If we pick a positive direction to the right, what we can do, sorry about that, what we can do is we can say plus 5 minus 1 is 4 meters. 4 meters, and since there's no sign, that's in the positive direction. So 4 meters to the east. Let's look at this one. This one's a little trickier. Oh, there's mine. I've got these in the wrong order. There you go. So I had 5 plus -1 is 4. So I added those two together. And what I did, I don't want to go too fast on that. I can also do this through the vector addition, the graphical thing, that first blue arrow to the right and that second to the left. I put them tip to tail and then drew the resultant in red. Okay, now let's look at the right. I walked 5 meters east and 1 meter north. That's a little different. My distance is still 5 plus 1, 6 meters. I don't really care about direction. I just talk about the total amount that I traveled. What's my displacement? Oh, that's really interesting. Well, we know from that, the Pythagorean theorem, I can't really do a frame of reference, positive, and use that to my advantage. The distance is 5 meters. The delta x, the displacement, is going to be that direct distance between those 2 points. So it ends up being how far I moved horizontally and how far I moved vertically, squared, add those, and then take the square root, 4.123. So I have to use Pythagorean theorem in that situation. We do a lot of problems, displacement, velocity, momentum, forces, where we have broken things up. We used components. We solved the x problem and the y problem, and we had to put them together again at the end. And this is an example of what we would do at the end of a problem where we'd separated variables. Okay, so in this case, my displacement, the magnitude of my displacement is 4.123 meters from the Pythagorean theorem. We also want to find the angle between that vector and horizontal in this case. And to do that, it'd be the inverse tangent of opposite, the 1 meter, over adjacent, the 4 meters. And the inverse tangent there is 14 degrees. We're going to see that over and over and over when we finish up x and y stuff and we put them together.